Good evening, everybody. So one of the things we do at NASA in Earth science, using the unique vantage point of space, is explore. And that exploration leads to discoveries, and those discoveries lead to research to understand and protect our home planet for societal benefit. Okay. Now, we can explore the Earth spatially, in this case, the combined land and ocean biosphere together. And that's basically looking at Earth's primary producers. And what's really interesting is that in just a single global composite, we can actually see all of this dimension in the ocean biosphere and in the terrestrial biosphere. Next slide. Actually using a series of images or information allows us to not only explore in the spatial dimension, but in time. And we can use this information to identify long-term trends. Now, this is kind of unprecedented. So what you're looking at is the combined global land and ocean biosphere, and it's like watching the Earth breathe in Earth's primary producers. Now, missions like Terra and sensors like MODIS are celebrating a 20-year anniversary or a 20-year time series. And what that does is opens the door into looking at decadal changes in our Earth system. So that's truly unique. Now, traditionally what we use is passive ocean color radiometry, which is what you're seeing here, to actually look at the ocean biosphere. And this is only one piece of the puzzle. What passive ocean color has done is absolutely revolutionize our understanding of the ocean ecology and Earth's carbon cycle in general. But if we really want to open new doors, then we have to push the boundaries scientifically and in engineering and actually use some new scientific approaches in looking at things like our ocean biosphere. And so one of the limitations, I think, of ocean color remote sensing is that our scientists actually think it's incredibly valuable and critical for studying climate variability and change. However, it has to be used during the daytime. It can't be used at low solar elevation angles, and it has to be used in a cloud-free environment. Now, what you can lump on top of that is actually it has some depth integrated challenges. It can only see to the first optical depth in the ocean. And in addition, it's got some challenges when you have heavy aerosol loading. However, there are technologies that we can use when coupled with passive ocean color remote sensing, absolutely revolutionize our view of the ocean. Next slide. LiDAR is one of them. Okay, that stands for light detection and ranging. And in 2006, NASA and Kinéis together launched the mission known as Calypso, which is a cloud aerosol LiDAR. And the main sensor on board of it, Calliope, has orthogonal polarization. And so this has been, it's supposed to be the Calypso animation. Sorry, you guys, just back up one. So what you're actually, so Calypso has been reliably providing global views of our Earth for over 13 years. Now, what's absolutely revolutionary about it is that it can penetrate up to 3 optical depths in the ocean. Okay, so whereas passive ocean color can only go the first optical depth. However, LiDAR data such as that from Calliope can only see a limited spatial resolution and has about a 16-day revisit, whereas passive ocean color remote sensing can cover the Earth in about 2 days. Taken together, however, they provide unprecedented scientific benefit for looking at things like dynamics in Earth's biosphere, specifically in the ocean. So we're going to talk about that in just a minute. I just want to also point out that studies of LiDAR have been used on both ships and on aircraft. And what they do is they use unique properties like the backscatter coefficient, the vertical attenuation coefficient, to look at things like phytoplankton properties, zooplankton, and even fish stocks. And this is important, very important properties of the ocean when we're talking about commercial viability and economics. So the other thing about LiDAR is that it is not limited by some of the things that limit ocean color remote sensing. You can use it day or night. It can deal with considerably heavy aerosol loads as well as thin clouds. You don't have to worry about low solar elevation angles, which I'm going to show you in a minute. And as I said, it can penetrate up to 3 optical depths. So this can be absolutely revolutionary in looking at our ocean. Now remember, I'm going to show you Calliope data in just a minute. And remember that it was not created to look at the ocean. It is an aerosol-based sensor. Okay, but it can give us unprecedented views of our ocean system. Next slide. So in 2013, what we did is we had the first global view of plankton in the ocean, not phytoplankton, not primary producers, but actually secondary producers from a space-based LiDAR. And we took this unprecedented information and we estimated phytoplankton carbon and particulate organic carbon. Now, these two ocean carbon properties together were derived directly from the calliope-based backscattering by particles. Now, remember, this was just a proof of concept study, right? This system was not created to produce anything in the ocean, and yet here we are. And so what we know from moving forward is that we can see into the ocean and tell something about Earth's biosphere. Now, that's not where it stops. Next slide. So I already mentioned that the sensor can function, or we can get data in the ocean at low solar elevation angles. And basically what that means is at about 81 degrees north and south, we can actually collect data. Whereas on the left-hand side, you see MODIS, which is passive radiometry. And what you're seeing is that we don't have a lot of coverage. Whereas Calliope on the right-hand side actually does. So what this study was able to do, this was part of the NAMES project, the North Atlantic Aerosol and Marine Ecosystem Study. They actually looked at Calliope data at high latitude and used a combination of the vertical attenuation coefficient and the backscattering by particles to detail what was going on ecologically in the ocean. And what they were able to determine, looking specifically at predator-prey interactions, was that in the northern hemisphere, basically at the northern polar, subpolar waters, the ecosystem dynamics were driving what was happening in the phytoplankton and in the plankton in the ocean. Whereas in the southern hemisphere, it was actually the ocean ice dynamics that were driving what was happening in the predator-prey interactions. And this was unprecedented and impossible without using the LiDAR in the ocean. So let's take things just a little bit further. Next slide. Now, the other thing that the NAMES team did, going out specifically looking at a number of objectives, one of them was what's driving phytoplankton blooms in the ocean. And you might be saying, why should I care? Well, as primary producers, they're consumed by secondary producers and fish. And if you know anything about fisheries, just taking that one economic aspect of the ocean, it's more than $1 trillion economy worldwide. Okay, so they did a transect in ships and with an aircraft flying overhead with a LiDAR, going from about 35 degrees north and straight northward, although this is, I think they had some wiggles in there. But what I want you to notice is that they were able to detail oligotrophic waters, which means they're almost devoid of nutrients or very low nutrients, which makes it very difficult to support phytoplankton and plankton in general. They went straight through a phytoplankton bloom, which you're actually seeing in the vertical attenuation coefficient. So this is the LiDAR showing this. And then they went into mesotrophic conditions where they have low productivity, but some going on. Now, let's zoom in on this a little bit. Next slide. And take a look at the eddy that they went through. So if you look at the top panel first, you're looking at the backscattering by particles derived from the Calliope sensor, okay? And what you're seeing as you travel across is the evidence of the eddy right here, of the physics driving the biology. Now, how do we know the physics are driving the biology? Most physical oceanographers will tell you everybody knows that. But we're going to actually detail this with a LiDAR. Remember, you're looking at the backscattering by particle data from a LiDAR, not actually any ocean physics measurements. If you look now on the bottom panel, what the team knew, actually first on the top, is that some dynamics were going on in that eddy. And they knew this because on the ship, they had a flow-through system that told them they had a high concentration of phytoplankton in that area. So what they did is they decided to look at the depolarization ratio relative to the backscattering by particles. And what that does is it tells you something about cell size and what's actually in the water. And this was confirmed with instruments on the ship, but when they pass through the eddy, what you can see is a very strong signal here. And this depolarization to backscattering ratio actually enabled them to detail, confirmed by the ship-based measurements, that they had different groups of phytoplankton there. And that becomes very important when you talk about biodiversity in the ocean. And let this sink in a minute, people, because this is kind of mind-blowing. We're using a LiDAR that was not created to look in the ocean to actually detail community structure, which is not even something we can do from passive ocean color yet, okay? So let's go further. Next slide. Okay, so this is sort of the like ultimate punchline. What you're seeing here is the largest animal migration on the face of the planet, and it happens every day. Okay, so we are looking at what's called diel vertical migration. Zooplankton are secondary producers. People have heard of phytoplankton. These are actually zooplankton. And what they do is they migrate every single day approximately 200 meters to the surface to feed on phytoplankton. Phytoplankton are primary producers. They go up to the surface. They need sunlight to actually go through photosynthesis. They take up carbon dioxide. The zooplankton consume them, and they excrete whatever they excrete, and that carbon goes to the deep ocean, a lot of it permanently. So what you're seeing is a conveyor belt of carbon. Now, what this actually is the global climatological signal of vertically migrating animals in a normalized differential ratio. Now, what does that mean? Basically, there are day-night differences in backscattering by particles, and this tells us something about vertically migrating animals in the ocean. Okay, so you're seeing that conveyor belt of carbon. And where the zooplankton tend to go is in clear waters, okay? That's because there are less visual predators there. This is a little bit counterintuitive because you would think they would be found in highly productive waters where there are a lot of phytoplankton that they can eat. So ecologically, what you're seeing actually makes sense, okay? And if you look between the two yellow lines, that's basically the permanently stratified ocean. So where we're seeing the high signal for the zooplankton and the lower signal actually corresponds significantly to what we would expect ecologically. So last slide. That's kind of mind-blowing, people, that we can't do that with ships, but we can do it with a LiDAR. So the future of LiDAR, where is it going? We have never built a LiDAR for the ocean. No one has. And clearly what this tells us is this, with some minor modification to future LiDARs that are being planned for the atmosphere or not, we could actually detail the profiles of ocean particles in the ocean. And what these figures have actually shown is that we've got the first ever view of vertically migrating zooplankton on a global scale, which is unprecedented. Thank you.